Alright, welcome back. We are at third, I think, yeah, the part 3 for this class. There will be 4 parts in total. So this is part 3, so halfway there. So for the last 2 parts, we talk about the first topic, right? I think you can see it here, which is the null hypothesis. What is a hypothesis, and why do we have to set this up at the beginning before we can do something meaningful? The second part is about the p-value. Okay. So we say that okay, we can make any hypothesis we want, but we have to kind of like transform that a statement or an experiment into a number or something that we can measure and make some meaningful decision on, and that number is a p-value, and that which we define as the area to the left or to the right, depending on what the original null hypothesis is. Okay, so if we believe this is greater than 1,000, okay, so that means we believe it's on the right hand side. Okay, so that if the number if the sample mean falls below 1,000, if it falls below not too much, then it's still possible, 999, 998 or whatever number. But if it falls below too far, that means our original null hypothesis is likely to be false. We get the wrong number. It's not supposed to be 1,000. Okay. So now we are gonna combine these two concepts, right, and make it a rigorous procedure, right? Make it like a list of several steps that you can perform. So, and that steps is what we call the hypothesis testing, right? So what it means is, it simply means what it is saying, like you test your hypothesis. You have a hypothesis and you have to test it. How do you test it? You collect a sample, right, and compute a p-value, and use that p-value to test your null hypothesis. So let's look at how we should do that. So first of all, we get a p-value. That's a value. The value itself might not be meaningful, so we have to add something to it. So we have to interpret what that value tells us about the population, and so we have to set up kind of like a threshold, like a mark that kind of distinguish between the sample mean or any data that is likely and those that are not, that are less likely. And that threshold, that line, is what we call a significance level. It's a level. It's high or low. Its significance is mean we want to like get a threshold, get a gauge that distinguish between the values that are common, right, and the value the value or the data that are less significant or less likely on the different side, and we are going to denote that as an alpha. So if we have this bell curve on the right, so we're gonna put a gauge here somewhere with the value alpha, right? And that's gonna be the gauge that will divide the regions into 2 areas. The area to the left, the area to the right, right, which is the part where we would not reject. So we still hold on to our belief that H0, H null, or the null hypothesis is still true. Right, if the sample we get falls in this area. Right. On the other hand, if the sample provides a number that is significantly different from what we have believed, which is that area, right, we believe it's something here, but the result is against it. The result tells us otherwise. We believe it's here, but the result says, oh no, it's all the way to the left, it's too far. So in this area, we are going to reject H null, reject what we have believed, So that's that's alpha is going to be the gate that divides the numbers between those that we do not reject and those that we reject. And what we are saying here is what we call a policy. Policy is like some kind of written agreement that we have to agree on at the beginning. That okay, if whatever happens, we will follow this policy. We will look at the risk and see how we would react to any kind of situation. Okay. So the policy is simply as like if the p value is less than alpha, we reject the null hypothesis. So that corresponds to the pink area, right? If the p value, whatever that value is less than alpha, and that alpha is what we are going to set up before we take any samples. Right? If that is below alpha, we reject the null hypothesis. So we think it's not true. So what is alpha? Alpha is actually any number we want to put in between 0 and 1. We might want alpha to be high or low. It depends, but usually we want that alpha to be low. Okay. But it have to be low. If it's too high, let's say I don't know if alpha is 0.5, and once we have put everything into the graph, okay, the graph will be something like that. If alpha is 0.5, it's halfway the curve. Okay. If p value is less than alpha, we are going to reject the null hypothesis. And that's okay if you want that to be very strict. Maybe you really don't want to have any tolerance. If you firmly believe that the mean is at least, let's say, 100, you may say, okay, whenever we see a number less than 100, we just reject the null hypothesis. We just believe that our original assumption is false, and that's fine if you want to be strict, right? But what you have to keep in mind is alpha is going to be the error in terms of percent. If you want the error to be 50%, then alpha is going to be 50% or 0.5. So that's alpha is going to be the probability of type 1 error. Or if you recall the table we have long time ago, we have this table, not long time, last week. We have type 1 here. We have type 2 error there. We say we cannot make these two errors be 0, sorry, or even like we cannot even make one of these to be 0 or too small. So these two numbers are going to be a little bit, not too small, but not too high. So this alpha is going to correspond to that entry on the bottom left. Okay. And that alpha is going to be the probability that we gonna commit to type 1 error. And usually alpha is going to be like 5%, 10%, 1%. Those kind of like sharp number that is easy to compute. So what will happen here? So there are going to be two branches, right? Let me. Oh, yeah. I think I can copy that whole thing. Ouch! No. Let's use a mouse instead. Can I move that down? No. 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 Can you get? Okay, cool. Let's move that down to this page. So this is what I mentioned before. Also, get rid of the pink one here. Pink one here. And shade that area green. So if alpha is, oh yeah, sorry, that's a mistake. That should be less than or equal to. That should be greater than. If alpha is less than or equal to the p value, or in this case, I should add that if the now hypothesis is a form of greater than or equal, is some parameter greater than or equal to that to some constant. So we believe that it is here. So if alpha, if the number is less than the p value, which is the pink area, we reject h now. So that means from our sample data, is it significant enough to tell us that the original assumption is way too off? It's not accurate in the first place. So we believe that was false, and that means we will believe the opposite, which is that h of 1, we believe that that number is less than x0. Here we don't know yet what is the actual population, mean or actual population parameter is, but we are sure that it's not going to be that x0, it's going to be way less than that. I think the first case, if it falls into the pink area, otherwise if it falls into the green area, that means that value, that sample still agree with our assumption. So the sample, oh yes, written here, there anyway. So the result are not significant enough. It means they still look similar to what we have believed is a null hypothesis, so that we don't have enough evidence to decline or to believe otherwise. We believe H null at first, and from that one sample, that's still kind of agree. That doesn't go against the original one. So that belief is still there. We don't change anything. So that means we do not reject. Again, we don't accept, because we have already accepted that. We have already established that to be true. So we simply do not reject. Just put it there. And I think that's, oh yeah, that's supposed to be typo. That's a H1. That's again H1. No. So it's on identify. So once we have the p value, right, and once we compare that p value to the alpha, then we can say we can come up, we can conclude our decision on whether we want to reject or not reject the original null hypothesis. So let's take a look at one example here. So for this example, we have the null hypothesis, we have the alpha, and we have the p value. So usually you have to compute the p value yourself. Okay. But just for the sake of, just for this section, let's say we get the p value already. So what do we say about this hypothesis? Okay. So you just say, okay, so what do we have to do here? We have to compare alpha with the p value. Okay. We have that curve, right, which whatever mu is it 1,000? We don't know what the sample gives us, but we know that from that sample it gives us the p value of 0.02h, and we put a gauge here at some value. Oh yeah, it's I think I make this to apps. So we have to graphs. Okay, we have that graph from our sample, and we get some x bar, whatever it is, and from that sample we compute the p value down here, and that p value is going to be between 0 and 1. So let's say in this case the p value is given to be here about 0.028. It's 0.028. But then our significance level or our alpha is 0.5 is here. So you put a GAD here, and we say if the number is greater than 0.5, we will not reject the null hypothesis. If the number is less than 0.5, we are gonna reject the null hypothesis. And in this case, it is easy to see that this p-value falls below that 0.5 here. So we simply say since the p-value is less than alpha, then we reject the null hypothesis. Okay. So if you are already given the p-value and alpha, then you can simply just compare these two. It is greater or less than or equals to. So we simply say we reject. That means we think, like from that sample, we think that it is false. Actually, let me get give me a moment. And I'm back. Sorry, it's getting hot, so I have to turn on my AC. So we say that we just reject H null. Right? We believe it's false. That means we believe in the opposite of that statement. So we believe in the alternate hypothesis that this mu has to be less than 1,000. Yeah. And that's all we know. Again, we don't know if it's any number. We don't know if it's if it will match our sample mean, but it has to be somewhere smaller than that number. Okay, simple enough. Right. So again, just changing some numbers and try yourself. See if you understand how we state our decision. So in this case, again, we have. Let's think about the graph. Like we have this graph, which we believe that the mu, the population mean is at least 20. It means that if the value falls below too low, like that, we're gonna reject it. If it's too low, then we have to get what we call the p-value. From that number, that will gives us a p-value. In this case, it gives a p-value of 0.12. So that's a p-value now. And where is our GAD? We set a GAD at alpha equals to 0.1. So that's the GAD, 0.1. So you can see that this case is the opposite of the previous one. So we can simply say since the p-value is greater than alpha, we decide that we do not reject H null. So it's just one sentence, right? If you have been given the p-values and the alpha, the significance level, then we can just compare them and say, and follow our policy to reject or not reject. And then again, that's gonna be simple enough. So let's see what should we do here? Like from this flowchart, we see that okay, if eventually we want to perform the hypothesis testing, we are going to follow this arrow. Right? From the sample, we get some information from that as center or the mu, the average or the spread as sigma or standard deviation, and we're gonna infer something from that with help from our friend in math department, the probability guy, okay? And that we can perform the hypothesis testing and derive at the final decision. So that's the whole process of statistical sampling. So, but that's one thing. There's something missing from the graph, right? And we'll see in a moment. But let's take a guess and where or when should we state the null hypothesis? Like where and when should we do it before we get a sample, or after the get? Should we perform that here before we get a sample, or after we get the sample? Maybe we want to look at the sample and look at the numbers and then set up hypothesis however we want to, or do we do it here? Just before we do the math, or do we do it here just before we make decisions? That should be 1, 2, 3, 4. So cast your votes on Google. Sorry, just kidding. Actually, I want to do something like that. There is a channel called Free Brew One Brown. They are teaching math online and they have like a live poll. That should be fun and engaging for students, but we don't have one too now. So let's take a guess. Where should we state our now hypothesis? 5, 4, 3, 2, 1, boom, time's up. And the answer is here. We had to state that all the way at the beginning before we even get a sample. So let's say why we do that. Let's go to the common misconception, which is here. If your answer is D, then you are not alone. That seems to make sense, right? So let's say like I take a sample and get some numbers, and someone says, okay, there's like, let's say there's 1%, 0.1% chance that, I don't know, your plane will crash. Right? If someone's after all these numbers, someone tells you that there is a 0.1% chance that your plane, wherever you are traveling to, will crash and burn and explode or whatever, then you get from that number, you will decide for yourself whether you want to fly or not. Okay? Maybe it's too risky because of the thunderstorm or snow or whatever kind of catastrophe. So maybe from that number you decide, you will decide either to just continue and take the plane and say just hope you are lucky enough, or you say okay, that's too risky and I'm gonna stay home and wait for the next flight tomorrow, next week or whatever. Right? That's common. Right? That sounds intuitive, right, for us human. But the truth is, like if you wait until you get the number before you make any decision, then that kind of decision will not be deterministic. Meaning that if one day I tell you you have 0.1% chance, maybe for this case, for that day, you say okay, you stay home. Okay. Maybe next week you are trying to fly again, and someone tells you that okay, we are a little bit luckier this time, and the chance is up to 0.5 now. Sorry, we are unluckier now, and the chance is now 0.05 because the weather gets worse, or because no one wants to fly, or whatever. Right? Then you say okay, you say that's higher, so I should stay home again, right? And again, maybe next time someone says the chance is now dropped to 0.05, and from that number you still have to make a decision if whether you want to continue on to your journey, or just again to stay home. Maybe you say, okay, that's smaller than last week or 2 days ago, so I should fly. But maybe you still think that number is high enough, so you should still stay home, right? So the problem with this kind of decision is that you make a decision on the spot. You make your decision after all these numbers are computed. So that decision will based on your feeling, not on math or not on any policy. It's gonna be based on this. All this decision is gonna be based purely on your feeling. Maybe it's not even the number itself, right? If you think that the chance is low, but then you just watch a television and you just watch a television and you saw a news that some plane crashes, then that news will affect your ability to make a decision. And you say, oh, someone is that plane crashes, so that means I shouldn't take any plane today or tomorrow, right? Because this is based on your feeling, then it is easy to be manipulated by other sources, from the news, from your friends, from social media, or wherever you check your news daily. Right? So that's gonna be a problem if you make a decision based on the number you just heard and just use your gut feeling. So that's why we cannot we cannot wait until at the very end to make a decision. So we have to make a decision at you have to make put a threshold, make a policy at first. So it has to be here, right? Way before we even take any sample. So again, you might ask, can we do it here now? Actually, right? Because if you don't see any sample, then you have no idea what the means would be. Maybe you are totally clueless and say mu is at least 10,000, but your first sample says that the sample mean is 10. That means in the beginning you are way too far off, because you have no initial information to make a good hypothesis with, right? And if you start here, if you state your hypothesis here, then again that is going to be affected by the number from the sample. And maybe if you see the number 10 and you think you want to be right? You don't want to be wrong. So maybe after you see that number 10, or that should actually be here. Let's say you get X bar here, right? Once you have compute anything, get the center, get the spread, you get the X bar here. Yeah. So if you say X bar is 10, you may want to be right and play safe and say that mu should be 9 at least, right? That somehow works, right? But then since you are right, the original testing is now pointless, because you are right. You see the answer. Just if you are on a quiz show, right, and then you see the answer, and then you use answer to you think of that answer as your answer, then you are right. You are going to be right. You are going to be correct. Then what's the point of being correct? If you want to also be correct, then you can just ignore that part and just use your gut feeling. If you want to always be correct, but that's not how any scientific method works. Right? So it's meaningless if you make the hypothesis after you see the number, because that means you are gonna be right, and if you are always right, then what's the point, right? Then you might want to come back here. Okay, this one is actually still a good candidate. Okay. Maybe after we get a sample, you look at the samples. Right? Since maybe the sample size is still large, you cannot compute all the spread and center in your head. Right? Maybe you see the raw data, 100, 111, 112, 13, and so on. You see that raw data, and then you make your hypothesis based on that raw data. Maybe you look and think, okay, that seems right, 100 each. Okay, so you think, okay, it's at least 100. Maybe after you get the number, you could be wrong. Okay, that will work too. But then again, if you look at the raw data, then you are already biased because you see you kind of like see the result. You get some idea for the result already, and if you base your decision on, if you set up your now hypothesis after that result, then again you are gonna be pretty almost aware, right? Because you see those already. So that number is gonna tend toward whatever you see in the raw data. So if you do it here, like right after you sample, it's gonna be biased. So that's why to have a rigorous process, you have to start your now hypothesis at the beginning, way before. But then you might ask, if you do it here, then what number should we put here? Right? If you're really like clueless on what the result would be, what would you put it in here? If let's just say you want to measure the average height of our students in TU Thammasat University, you will be like totally clueless, right, on how to put that number in. Maybe you put, I don't know, 150. That looks like around a nice number. And then from that number, you might be right or wrong. You might be totally wrong. Maybe the average is much lower than that, right? But then the question is, how do you get this number, right? And the answer is, you get this number from, let's guess what? From previous experiments. So that's gonna be like kind of a loop here. So you get this number from previous experiments, right? Or from other sources, from other experiments, or other hypothesis testing. So maybe you want to measure the average height of students in TU, right? But since you have an idea, then you might want to get some number, and you might get that number as an average height of all the students in Thai colleges. Right, now you have some number to start with, to work with, or you might get the average height of like even all people in the universe, or adults in Bangkok, in Thailand, or whatever. Right, you're gonna get that number from whatever other sources. Of course, you can put in a random number if you want to, but that again gonna be useless. So you have to have some rough idea here, right? And that idea is gonna come from other source, and you use that source to test if the number from other source would work with this specific case, and if the average height of all students would apply to the average height of students in this particular university, which is the Thammasat University. And so that would be the way we do it nicely and correctly. You may want to add some number, or maybe you believe the average should be. You maybe you see your friends and you think, oh, they look tall, so the average should be slightly higher than the average for all students. So you can now you can put any number here, right? Which you believe that should be the deviation or the difference. Now you can adjust that a little bit, right? But the baseline, the number itself, should come from other sources. Other sources, and I should add reliable sources. You don't want to get that from GAD or whatever random sources. So yeah, so now you have a number from somewhere else. You may plus or add or subtract that to whatever the difference you believe in, and now you can use that number to test whether your original hypothesis or your null hypothesis is true or not. Yeah, all right. Oh, and you have to state both the hypothesis. Oh, you have to state both the hypothesis and the significance level. You have to have them together. You have to put some number here, and you have to also state that what your confidence level. What your significance level is, where you would put the GAD to distinguish between the sample data or sample mean that is likely and those that is not likely or less likely. So you have to have these two things in mind before you start to take your samples, so that the sample will not affect your original decision. There will be no bias in your experiment. So here it will look pretty similar to scientific method, if you remember from high school. Okay, so you have to first set up your hypothesis, and you have to set to contradictory hypothesis, which is H0 and H1, and also state exactly what the significance level is. Where should you put the GAD? How much type 1 error you want to tolerance, and then from the second step you collect the sample data, which is here. I take the data, and yeah, that's as an addition in homework problems, or in mostly in homework problems you get the data already, because in homework you just have to only understand the concept. You don't have to do the hard work of getting all the numbers correct. Once you have the concept correct, then you should be doing fine when you are faced with the real problem. Yeah. So once you collect the sample data, then you have to determine the correct distribution. In this case, that could be up here or below there. So it's kind of interchangeable. If you know that you are taking the data about the mean, about the sample mean, then that means, since by the law of large number, you know that mean is gonna follow the normal distribution here. Okay, so you know the distribution even before you collect. But sometimes you don't. Sometimes you plan to take 100. You plan to take a questionnaire from 100 people. Right, and since that number is high enough, then you can assume that the mean, the average, is gonna follow the standard, the normal distribution. But then for some reason you don't have enough time, because COVID or because any random scenario, then you only get 25 people. Right. And since 75 is too low, the size is too small, then you can no longer assume that For a small sample size, you have to use a different distribution called again the students t. That's the distribution based on the size of the sample. So sometimes you can determine that in advance. Sometimes you can. But anyway, you have to correctly identify what kind of distribution you are working on. I think you see that here. No, maybe it was. Yeah, it was up there. So once you know what kind of distribution it is, then you can draw a graph yourself. You get a mu0 here. You get x bar from the sample. You can compute the p value, and then from that p value you see if it's smaller or larger than alpha. Right, so that's the step 4. You analyze this. You get the mu, you get the x bar, you get the standard deviation, you get the proportion, you get whatever you want to, and then you get the p value, and then that would give you something that you can decide. Right. Instead of a problem about your feeling about whether it's right or wrong, it turns into a problem of mathematics, whether that value is greater or smaller than the alpha or whatever value it is. Right. And then at the end, at step 5, like, you make a decision to reject or not reject. So you have to follow this 4 steps in order. And that you can see here that again we have to set up the hypothesis before we start to collect the sample, so that we wouldn't be affected by the sample themselves. So let's take a look at how do we perform that kind of test. Okay, so in homework and in here, in the real world problem, then the statement is gonna be this kind of like wall of text, where you have a bunch of information, a bunch of data, and you have to conclude with some thing, get some meaningful decision, right? So in this case, for this example, you are asked to carry out the whole hypothesis testing, right, from the beginning to the end, except the second step. Yeah, that we see the score already. Right, so the statistics students believe that the mean score on the first test is 65. Right. For the students, they believe that 65 out of maybe 100, because the exam is hard, or because the instructor fails to explain clearly what the exams or what the problems are. But on the other hand, the instructor thinks that the mean score is higher than 65. Right, so now we have different groups of people, 2 groups of people, and they believe on different things. So one of this is gonna be true, and the other one is gonna be false, and that corresponds exactly to the null hypothesis and the alternate hypothesis. So let's start with the step 1. Let's ignore the rest of the text first. That doesn't work. So we have to set up the null hypothesis here. And let's see which way I do in the lecture. The way you set up the null hypothesis is, you can do it either way. Okay. You can start with your belief, or you can start with students' belief. Just make sure you start with one. And which one you think that is more likely to happen? So maybe you think that, okay, since you believe you are right, then you are trying to reject the other hypothesis. You are trying to reject the student's belief. So what we do here is we set up the null hypothesis to be less than 65. And because this is something that we are trying to reject. And then again, it depends on how you approach this problem, but it is also correct to do it this way. There's nothing wrong if you start with mu greater than or equals to 65 in the first frame. That's still fine. We are gonna derive, we are gonna have different conclusion, but both works. In this case, let's start with less than or equals to 65. Because we are trying to, in this case, we think that we should like kind of like deny students' belief. So that means the other one, the alternate hypothesis, is that the mu is actually greater than 65, which is what we as an instructor believe. So that's step 1. And step 2, and also we have to establish the confidence level. And in this case, we use 5% because that's the standard number, and that corresponds to 0.5. So now step 1 is done, right? We set this up before even look at the data, like before you even have any idea of what the numbers are. Then step 2 is here. Is this when we get that result. So now you collect a sample. Maybe there are 100 statistics students, but you only collect 10 because you just want a sample to test. So what do you do here? That's a raw sample, right? So you have to get the x bar, and you have to get the standard deviation. I think x bar in this case, you just sum this thing up, like 65 plus 65 plus 70 plus 67 plus 66 plus all the way up to 71 divided by the number of the sample size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I am doing this correctly, that will be 67. And that's 67. And oh yeah, I forgot to put in the S here. You then have to compute the standard deviation. And in this case, that would be square root of summation of xi minus x bar square divided by n. And whatever number it is, that will give us something that we can work on now. Okay. So that's step 2. We get. I'll tell you that we have already performed step 2 here. Okay. And actually, before this is actually step 4. This is when we analyze what we get. But then we are missing a step 3 here, which is to determine what kind of distribution we are working on. Since this is mu, it is usually the normal distribution. And by the law of large number. But since the sample size is too small, since we only have 10 students, right, so we have small sample size, and that means we have to actually use the other one called the students tree distribution. I think you can go all the way up. Yeah, here. Okay, so it's gonna be this formula. Right. So whatever, you just use this formula instead of the one at the top. Okay, so where are we at now? Here. Okay, so since we know that that's the T distribution, I think let's say x bar minus mu divided by s over square root of n. Yeah, something like that. And from that number, it's gonna be this distribution, whatever it is. We know for sure that it's gonna be some kind of curve, right? It's gonna be, we're gonna have that 67 here. Oh, it's the other way around. Okay, so that's mu is, which is 65. Since our original now hypothesis is that it is less than or equals to 65, so we believe that this is true. This is what we believe. That means we will reject if the evidence is against our belief. So we will reject if it's too high. In this case, the graph is flipped to the other side. If it's too high, then we will reject. But now what we get here, we get number 67. The question is 67 too high? We want to analyze and determine whether it's too high. So what we do here is we compute the area of this curve using an applet or calculator, or use your math friend to get your number. And so once you have that area, and then that area will give you the p value. So I'm just gonna skip the computation part because that's not fun, one thing for sure, and also because that's like kind of a routine. It's like, okay, you plug in that to get a t, the value t somewhere. You get a 0 here, you get a t here, and then you find the area. Like it's still the same idea, as long as you understand that we are trying to find the area to the left or to the right of that curve, then you are doing fine. So now, in this case, there is, that gives us, so let's repeat that we are performing the student's t test, and that is something like that, formula, whatever it is. And since the student's t-test, that test depends on the sample size, and so we have to add another parameter here, which is the degree of freedom. And again, I didn't teach this. It's just like, if you understand that, okay, you have to get that number and just plug that number in your calculator. But then, yeah, in this case, you also need to use the sample size. And since there are 10, then that number is 9. And so now you use that value, and that value will be computed to be minus 1.95. So you use these two numbers into your laptop website or whatever it is, and that will give you the p value. And again, you don't have to know exactly what the formula is, but you have to know that we are trying to get the p value, and that value is the I think I flipped the curve somehow. Okay, yeah. That's supposed to be plus 1.95. I'm gonna fix this slide. So that means that's supposed to be this curve instead, right? The center is 0. This t is 1.95. We are trying to determine whether it is too far away from the center. Yeah. And by that we mean we want to compute the area, if the area is too small or not. And so that means we are trying to find this p, this probability that the area of the curve. And if you put that in the whatever tool you are using, you are gonna get 0.03696. And so we can say now that the p value is 0.0396. And that's step 4 you can say this step 4 is pretty long because we have to deal with numbers, lots of numbers, and formulas, and So now that we get, that's what we get from step 4. And then step 5, here we have to go back and see what our policy was. Right? Since we established the significance level, the alpha to be 0.05, then we are saying that we only reject, right, if the result is significant enough, if the result falls into this small region. Okay. And in this case, yes, it is, because that number, the p-value, is less than alpha. It's somewhere here, maybe about 0.04. Right. Oh, by the way, yeah, in this case, again, it says that there is 3.96% chance, right? The p-value itself has some meaning, right? But and that meaning is that there's the 3.96% chance that a random sample will give you the mean of 67 or more. There's this chance that the x bar is gonna be at least 67. Right? That's 4% chance that it's gonna be high. Right? And since that chance is small enough, and by enough it means it is less than our significance level in the first place, that means we go back and say that, okay, in this case we decide to reject H now. We reject the hypothesis now. Why do we reject? Because when we look at the curve, if we were correct, then it is, the mu is 65. Right. We believe that the average is at most that number. But this single evidence, this single sample is against this sample. The sample says no, the number should be higher, and that number is not just like a little bit higher; it's just like pretty high from the baseline at 65 that we set up at the beginning. So that means we reject it, and that means we believe H1 instead. Since H0, that we believe that the mean is less than or equals to 65. The opposite of that, or the negation of that, is that the mu should be greater than 65. So that's it. So that's the whole process of hypothesis testing. So let's take a quick glance here. First, we have to set up what our hypothesis is. Oh, by the way, for the text here, right? This text should be above the sample. Okay. It's wrongly put here because you should get that number 5%. You should get the number alpha 5% before you get any samples. Okay. So you set up the hypothesis here. In this case, since you believe you are right, then you are trying to dispute the student's belief, and this is the student's belief. Okay. So you say, okay, let's say that you guys are right, and then I'm trying to disprove you. I'm trying to say that what you believe is false. Okay. And so we carry out the step 2, 3, 4, and 5. And step 2 is to collect samples, you get 10 numbers. Step 3 is to determine what kind of distribution it is. In this case, we get the student's t. Step 4, we analyze. We get x bar, we get s, we get degree of freedom, you get the t value, and eventually we have to get the p value. That's the goal. And now we get the p-value in step 4 when we analyze. And then step 5, we look at the p-value and we look at the alpha and see if we should reject or not reject the original null hypothesis. Oh, that's kind of like a long way, right? But if I break this into like several small steps, it should be, I shouldn't assume that. Right? It should be like kind of easy to follow. But besides step 4, that you have to use calculator and you have to put in the right number. Right? It's gonna be frustrating because sometimes you put in the wrong number. I mean, step 1 makes sense. Right? You have to put this first. Step 2 again makes sense. You have to take a sample, or otherwise you cannot prove anything. Step 3, just to make sure we are working on the right path, the right distribution. Step 4 is a long step that we get all the numbers and finally we get the p-value. And step 5 is to decide to reject or not reject. So that's just one example here. And there's gonna be kind of a short run on the exams. Oh, sorry, yeah, both exams and both homework. And since I think that step 4 is kind of frustrating, I will try to give you something that is easy to work with, or I try to give you the numbers that you don't have to calculate too much. And we finish that, right? And this is kind of like a side note here. For the first 2 parts, here and here, we only look at the case when the now hypothesis is of the form mu is greater than some value here. So we believe that the average is in this area. Okay. But since we don't have to like just stick on the greater than or equal to sign, okay, we can change it to other forms. Okay, we can change it to that the less than. Oh, let me separate that. Okay. That will look like that. Right, so we believe in the green area, right? And if the sample or anything goes against our original assumption, then we will reject H now. Now, if the original statement is that mu is less than or equals to some value, mu 0, mu null, and then in this case, this is what we work on for the previous example. We believe this is true. We believe that the average is to the left of this point. That means we will reject our now hypothesis if the values are too high. We believe it's small, but if it's a little bit too high, then we still believe we are correct. If it's way too high, then we will reject H now. And finally, we have H now that we believe that mu is equals to mu naught. Now, note that for this one, it will look weird if you think about it. So we believe that the mu is exactly, let's say, 504. And yeah, sure, you can believe that, but then from the probability point of view, you are gonna be wrong 100% of the time, because there is like almost 0 chance, or actually literally 0 chance that you are gonna be right. You believe the mu is 504, but maybe it's like 504.1278 or whatever random number it is. So this statement looks kind of weird. And I think it's weird now, but this is like how statisticians work on problems. So I don't understand. array. So we believe that what it actually means is we believe that this is approximately mu0. When we write it, we write it as mu equals to mu0. But what we actually believe, what we are trying to say here is that mu is approximately mu0. That means we believe that if we put a mu0 here, we believe that it shouldn't be too far from that center. And you can see it expands on both sides. Right. For the greater than or equals or the less than or equals, that makes sense. Right. Mathematically. And for this one, what we have in mind is actually this kind of image. Right. That it is around this middle mu0. So if we believe that the number shouldn't be too far from that mu0, that means we are going to reject, we are going to disbelieve, to disprove ourselves if the values fall below way too far from. Now, from both ends, oops, from both the left side and the right side, if it's too far from either side, if it's too high, or if it's too high, or if it's too low, then we're gonna say, okay, that center should be wrong. So now that's the kind of the difference, and the part that like makes that sense. But what it means here is kind of a little bit different from what it is expressing in math terms here. Okay. So we're gonna have these three types of tests, and if you understand the concept, right, you don't have to memorize these images. If you understand the concept, then you can just start from scratch. You can always start from scratch, right? And draw that, put a mu0 here, and then you can determine yourself if it's to the left or to the right or both sides. And I have written it here. There's some explanation there, right? Oh yeah, this is what we have done before. In this case, we call that a left tail test. Okay. Because since we believe it is to the right, we will test when it is on the left. And actually we test every value, we test every single sample, but we actually test like if it's on the left. Like if we believe it's 1,000 and a sample, say this is 1,005, since that agrees with our belief, then we don't have to like actually do anything about it, because 1,005 is maybe something here. Right? So you see the number, and then you don't have to like actually compute the p-value. Just the number itself will agree with our now hypothesis. So that means we will only test when the number is too far below to the left. Now in this case, we need to compute the p-value and other stuff. I think let's say move on. We see, okay, it's 1,005, and then oh, we are right, nothing to do here. And on the other hand, once we say a number that's below, then we have, okay, let's look at the p-value. Let's see if it's too small. And so that's a left tail test, and I think I explained that beforehand here. That since we have left, we gonna have right. And if we have left, we have right, we also have two tail, meaning they are both sides. For the right one, this is the same image that we had before. We have three areas. This part agree, this part does not agree, but still possible. And the part on the left is the place when we reject. If you want formula, that's the formula from x bar mu0 sigma n, you get a single number expressed in the form of the probability, and that probability is what we are going to use to decide to make a decision. And for the other side, if we believe it's greater than or equal to, we will test when it's on the left. If we believe it is less than or equal to, we will test it is on the right, and then again it should have here. That agrees. That does not agree, but nevertheless it's still plausible just by pure chance. Only when it's too far here that we think that evidence from the sample is against the null hypothesis. And lastly, we have two-tailed test. But one thing to note here is that for the two-tailed test, the p-values here are computed as the sum on both sides. Well, suppose that we believe that the average is 10,000. I think I use this number too often. Anyway, so let's say we get a sample of 995. Then of course we have to compute the area to the left. But also we have to we also have to compute the area to the right. Okay. Because again by pure chance maybe that number is 5 higher or 5 lower, and if it is very symmetric, then they are no different. Right? If we believe it's 1,000 and then we see it's 995, then we should be able to see and deduce that it is equally likely that the number is actually is gonna be 1,005. From that value, yeah, we get a single value here, but that also gives us the chance for falling into that area as well. And so in this case, the p value is computed from I think that should be a minus sign here. So the p-value here now has both ends, like both the left and both the right. Or you can just compute one side and multiply that by 2. You get the number. So that's one way to think about this. And the other way to think about it is, maybe this is more intuitive, but that's not what it in the textbook. So let's say we want that alpha to be 0.05, but we want to have only 0.05 error. So again, we have to set a gate somewhere right here. And since this is two-tailed test, right, we have to set 2 gates. So only when the value falls below that gate or goes above that gate, we will reject the original null hypothesis here. And since we have 2 chances or 2 places we reject, that means since we want the combined rejection area to be 0.05, that means each part only takes 0.025. We don't get 0.05 on both sides. Right, one is 0.0, we get half and half. We split it up. Now that's also 0.0. Oh, that's the area, not the point. The area of these 2 areas. The area of each of these 2 areas is 0.025. So that means whatever value you get here you actually compare that value. You don't compare that value to alpha. You actually compare that value, right, to alpha over 2. Did you get this right? Yeah. You compare that value by alpha over 2. If it's to the left, we have to, we want P to be above that threshold or that gate, and that gate is not 0.05. That gate is pushed to the left to 0.025 to the left, right? And also if you repeat the experiment, let's say that's P1, and maybe a different time you get P2 to the left. And again, you actually compare that P. You want that area to be less than. You want that area to be less than alpha over 2 also. Yeah, for the previous 2 cases, we compare that with alpha. But for the two-tail case, you compare P with half the alpha. And if you just rearrange that a little bit, then maybe you want twice the P to be less than alpha. So, right. And that's why we get the number of 2 here. I think this part makes more, this inequality makes more sense. Right now you want P to be less than half the alpha, because now alpha is split to 2 parts. If it's to the left, it has to be less than half the alpha. If it's to the right, it also has to be less than half the alpha. But the formula you see is here. Right, so there are 2 ways to think about it. Depends on whichever method you like. It's just one. Okay, so and yeah, let's take a break there and continue with the kind of the extra part for this lecture.